Hello there. I'm so glad you found your way here tonight. Right now, as you settle in, something remarkable is already beginning to happen. Your thoughts are loosening. Your muscles are softening. And somewhere deep within your mind, the machinery of dreams is quietly preparing for its nightly work. Every night, without fail, your brain creates entire worlds. It paints landscapes that have never existed. It summons people you have not seen in years. It tells stories so vivid that you wake with your heart racing, or your cheeks wet with tears. And yet, by morning, most of it has vanished like mist in the sunlight. Tonight, we journey into that hidden realm, the world of dreams. We will explore over 100 soothing facts about the science of dreaming, about why we dream, what happens when we sleep, and the strange and wonderful things our minds create when consciousness fades. There is no test at the end, no pressure to remember anything. Just the gentle pleasure of understanding your own sleeping mind a little better. So let your breathing slow. Let your body sink into wherever you are resting. And let these facts drift over you like clouds passing across a moonlit sky. The world of dreams is waiting. And tonight, we explore it together. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the mysteries of the sleeping mind. Either way, this space is for you. There is something deeply peaceful about contemplating the world of dreams. Every night, your brain performs a miracle. It takes fragments of memory, emotion, and imagination, and weaves them into experiences so real that you laugh, cry, run, and fly without ever leaving your bed. You are a dreamer. Every human who has ever lived has shared this experience. From ancient cave dwellers to modern scientists, we have all closed our eyes and stepped into worlds that exist only within our minds. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in. Let your breathing slow, and let the weight of the day drift away, like the fading memory of a dream. Dreams are patient teachers. They wait for us every night without fail. They process our fears, rehearse our hopes, and sometimes show us truths we had not yet admitted to ourselves. They are the brain's way of making sense of the world while the world sleeps. Tonight, we will wander through this magnificent landscape. We will discover why dreams feel so real, how scientists communicate with dreamers, and what happens in the brain when you close your eyes. We will explore nightmares and lucid dreams, sleep paralysis, and hypnagogic visions, and the strange ways that memories are woven into the fabric of our nightly journeys. But there is no hurry. Dreams have been visiting us since before we had words to describe them. They can wait a little longer while you rest. Let us begin with the great mystery of why we dream at all. We still do not know exactly why we dream. Despite centuries of fascination and decades of modern research, the fundamental purpose of dreaming remains one of neuroscience's most enduring mysteries. Every night, your brain spends hours creating vivid experiences that seem essential to health, yet scientists cannot definitively explain why this process evolved. Some researchers believe that dreaming is simply a byproduct of other important brain functions during sleep, while others argue that dreams serve specific biological or psychological purposes. The fact that virtually all mammals and many other animals appear to dream suggests the process has deep evolutionary roots. What we do know is that dream deprivation has measurable effects on memory, mood, and cognitive function, hinting at the importance of whatever dreams accomplish. The mystery of why we dream continues to drive research that may one day reveal the hidden logic of our sleeping minds. Dreams may help the brain strengthen and organize memories. One of the leading theories of dreaming is that it plays a crucial role in memory consolidation, the process by which new experiences are integrated into long-term storage. During sleep, the brain replays and reorganizes information from the day, and dreams may be the conscious experience of this behind-the-scenes work. Studies have shown that sleeping after learning improves recall, and that the content of dreams often relates to recently learned material. The hippocampus, a brain region essential for memory, is particularly active during REM sleep, when most vivid dreams occur. This replaying of memories may help transfer information from temporary storage to more permanent locations throughout the cortex. Dreams might serve as the brain's nightly housekeeping, sorting through the day's experiences and deciding what to keep and what to discard. Some researchers believe dreams allow us to process emotions safely. According to the emotional processing theory of dreaming, sleep provides a safe environment in which the brain can work through difficult feelings without the physical consequences that might accompany such emotions during waking life. Dreams often feature emotionally charged scenarios that would be stressful if experienced while awake, yet the sleeping brain processes them without elevating stress hormones to waking levels. REM sleep appears particularly important for this emotional regulation, as the brain chemistry during this stage is uniquely suited to reprocessing memories while stripping away some of their emotional intensity. People who dream about emotionally significant events often feel better about those events the next day. This theory helps explain why sleep deprivation often leads to increased anxiety, irritability, and emotional reactivity. Dreams may serve as overnight therapy, allowing the mind to heal from the emotional wounds of the day. Dreams might serve as practice runs for threatening situations. The threat simulation theory proposes that dreaming evolved to help our ancestors rehearse responses to dangerous situations, improving their chances of survival. This would explain why so many dreams involve chase scenarios, being unprepared for tests or meetings, or encountering dangerous animals or hostile people. By simulating threats in the safe environment of sleep, the brain may strengthen neural circuits that would be activated in similar real-world situations. Children and people living in dangerous environments tend to have more threat-themed dreams, consistent with this theory. The emotions felt during threat dreams, primarily fear and anxiety, are genuine, suggesting that the brain treats these simulations as meaningful practice. While we no longer face the same predators as our ancestors, our dreaming minds continue to rehearse the challenges most relevant to our current lives. Creativity may bloom from the strange connections dreams create. Many artists, scientists, and inventors have reported that breakthrough ideas came to them in dreams, or in the drowsy states surrounding sleep. The creative potential of dreams may arise from the way the sleeping brain combines information in novel ways, freed from the logical constraints that govern waking thought. During REM sleep, the prefrontal cortex, which normally filters and evaluates ideas, becomes less active, allowing more unusual associations to form. Famous examples include Kekulé, Baxter's dream of a snake biting its tail, which led to his insight about the ring structure of benzene, and Paul McCartney hearing the melody for Yesterday in a dream. Dreams may function as a kind of creative laboratory where the mind experiments with possibilities it would never consider while awake. The strangeness that often characterizes dreams may be precisely what makes them valuable for creative breakthroughs. The true purpose of dreaming may involve all of these functions at once. Rather than serving a single purpose, dreams may be multifunctional, simultaneously contributing to memory consolidation, emotional processing, threat simulation, and creative problem solving. Different aspects of dreams may fulfill different functions, depending on what the brain most needs at any given time. This would explain why dream content is so varied, sometimes processing recent memories, sometimes working through emotional difficulties, and sometimes generating entirely novel scenarios. The brain is an extraordinarily efficient organ, and it would be surprising if the considerable resources devoted to dreaming served only one narrow purpose. Understanding dreams may require accepting that they are complex phenomena with multiple overlapping functions. The full picture of why we dream may be richer and more nuanced than any single theory can capture. Most vivid dreams occur during REM sleep. Rapid eye movement sleep, discovered in the 1950s, revolutionized our understanding of when and how we dream. During REM sleep, the brain becomes intensely active, displaying electrical patterns similar to those seen during waking, while the body remains mostly paralyzed. It is in this stage that the most vivid, narrative, and emotionally intense dreams typically occur. The eyes move rapidly beneath closed lids, as if watching the internal scenes playing out in the mind. REM sleep accounts for roughly 20 to 25% of a typical night's sleep, occurring in cycles throughout the night. The discovery that REM and dreaming were closely linked opened new avenues for studying the sleeping mind scientifically. When people are awakened during REM sleep, they report dreams far more frequently than when awakened during other stages. REM sleep is sometimes called paradoxical sleep. The term paradoxical sleep captures the strange contradiction at the heart of REM. While the brain is blazingly active, the body lies almost completely still. The brain's electrical activity during REM closely resembles that of an alert, awake brain, yet the person is deeply asleep and difficult to awaken. This paradox puzzled early sleep researchers, who expected that deep sleep would mean a quiet brain. The intense brain activity is thought to reflect the complex processing that underlies vivid dreaming, including the construction of detailed scenes, the generation of emotions, and the integration of memories. Meanwhile, the paralysis of the body prevents dreamers from acting out the movements they are only imagining. Paradoxical sleep is one of the most distinctive and still somewhat mysterious phases of the nightly cycle. Dreaming also happens during non-REM sleep stages. While REM sleep is most associated with vivid dreams, research has shown that dreaming occurs during non-REM stages as well, though these dreams tend to be shorter, less visual, and more thought-like. Non-REM dreams often involve simple, repetitive scenarios or fragments of the day's events, rather than the elaborate narratives typical of REM dreams. Some people report their most disturbing nightmares during non-REM sleep, particularly during slow-wave sleep earlier in the night. The difference between REM and non-REM dreams may relate to which brain regions are most active during each stage. Understanding that dreams can occur throughout the night has changed how scientists think about the function of dreaming. It suggests that the brain may engage in different types of mental processing during different stages of sleep. A posterior hot zone in the brain predicts when dreams are happening. Recent research has identified a region at the back of the brain that becomes particularly active during dreaming, regardless of whether the person is in REM or non-REM sleep. This posterior hot zone includes areas involved in visual processing and the sense of space, which makes sense given the vividly visual nature of most dreams. By monitoring activity in this region, researchers have been able to predict with reasonable accuracy whether a person is dreaming before waking them to ask. The discovery of this hot zone has refined our understanding of where in the brain dreams are generated. It suggests that the experience of dreaming arises from activity in specific neural circuits rather than from the brain as a whole. This finding opens new possibilities for studying dreams by tracking brain activity in real time. REM periods grow longer as the night progresses. The architecture of a typical night's sleep means that REM periods start short, perhaps only a few minutes in the first cycle, and become progressively longer toward morning. The final REM period of the night can last 30 minutes to an hour, during which the most elaborate and memorable dreams often occur. This pattern means that people who are regularly sleep-deprived, cutting their night short, are disproportionately missing out on REM sleep and its associated dreams. The growing length of REM periods may reflect a biological pressure that accumulates during non-REM sleep and is discharged through dreaming. Understanding this pattern has practical implications for dream recall, as waking naturally in the morning often means waking from a REM period. The structure of sleep itself shapes when and how much we dream. Morning REM is especially rich in vivid and elaborate dreams. The last REM period of the night, occurring close to natural wake time, tends to produce the most detailed, narrative, and emotionally engaging dreams. Dreams during morning REM are more likely to feature complex storylines, familiar characters, and vivid sensory details than dreams earlier in the night. This may be because longer REM periods allow more elaborate dream construction, or because the brain chemistry of late-night REM is particularly conducive to rich dreaming. Many of the memorable dreams that people carry into their waking day come from this final period. The phenomenon explains why being abruptly awakened for an early alarm can feel particularly jarring, as it interrupts the most dream-rich part of the sleep cycle. Morning REM is like the crescendo of the night's dreaming symphony. Emotional centers stay active, while logical areas quiet down. During REM sleep, brain imaging reveals a striking pattern. The limbic system, which governs emotion, remains highly active, while the prefrontal cortex, responsible for logic and critical thinking, shows significantly reduced activity. This imbalance helps explain why dreams are often intensely emotional, yet lack the rational scrutiny we would apply while awake. Fear, joy, sadness, and desire flow freely through the dreaming mind without the moderating influence of our inner critic. The amygdala, central to processing fear and emotional memory, is particularly active, which may explain the prevalence of anxiety and threat in many dreams. This pattern of activation creates a perfect environment for emotional processing, allowing feelings to be experienced and perhaps resolved without the interference of logical analysis. The dreaming brain is an emotional brain, freed temporarily from the constraints of reason. The brain's inner critic relaxes, allowing dreams to bend physics. The prefrontal cortex normally serves as a reality-checking system, evaluating incoming information and rejecting impossibilities. When this region becomes less active during sleep, the brain accepts dream events that would immediately be recognized as impossible while awake. People can fly, walls can speak, and time can flow backwards, all without triggering the slightest suspicion. This suspension of critical thinking is essential for the immersive quality of dreams. If we constantly questioned dream logic, the experience would not feel real. The relaxation of the inner critic may also contribute to the creative potential of dreams, allowing unusual connections to form that would be filtered out during waking thought. When we dream, we temporarily inhabit a world where physical laws are matters of suggestion rather than necessity. Acetylcholine rises while norepinephrine and serotonin dip. The neurochemistry of the dreaming brain differs markedly from that of waking consciousness. Acetylcholine, a neurotransmitter associated with memory and attention, rises to high levels during REM sleep, helping to activate the brain regions that generate dreams. At the same time, norepinephrine and serotonin, which normally help maintain alertness and logical thought, drop to their lowest levels of the day. This unique chemical cocktail may explain many features of dreams, including their vivid imagery, emotional intensity, and disconnection from logical analysis. The absence of norepinephrine in particular may help the brain process emotional memories without triggering the anxiety responses that would occur during waking recall. Understanding this chemistry has led to the development of drugs that can enhance or suppress dreaming by manipulating these neurotransmitter levels. PGO waves ripple through the brain as vivid imagery builds. Pontogeniculo-occipital waves, known as PGO waves, are bursts of neural activity that originate in the brainstem and sweep forward through the visual processing centers during REM sleep. These waves coincide with the rapid eye movements that give REM its name and are thought to trigger the vivid visual imagery that characterizes most dreams. PGO waves essentially provide the raw material for dream scenes, activating visual circuits, even though no external visual input is reaching the eyes. The timing of these waves correlates with reported dream imagery, suggesting they play a direct role in constructing what we see in dreams. The discovery of PGO waves helped demonstrate that dreaming is an active process driven by specific neural mechanisms, rather than simply random noise. These electrical ripples through the sleeping brain create the landscapes we wander in our dreams. The prefrontal cortex quiets, reducing metacognition during dreams. Metacognition, the ability to think about our own thinking, is severely impaired during most dreams. The prefrontal regions responsible for self-reflection and awareness of our own mental states show reduced activity during REM sleep. This explains why we rarely question the strangeness of dreams, or realize that we are dreaming while dreams are happening. The lack of metacognition means that dreams feel entirely real in the moment, no matter how bizarre their content. This is also why lucid dreaming, in which the dreamer becomes aware they're dreaming, is relatively rare. It requires the prefrontal cortex to become unexpectedly active during sleep. The ordinary dreamer has no more ability to step outside the dream and evaluate it than a fish has to step outside of water. Theta rhythms help bind scattered fragments into dream narratives. Brainwaves in the theta frequency range, which oscillate at about 4 to 8 cycles per second, are prominent during REM sleep and appear to play a role in binding disparate elements into coherent dream stories. These rhythms may help synchronize activity across different brain regions, allowing visual imagery, emotional tone, and fragments of memory to combine into a unified experience. Theta waves are also associated with memory processing and spatial navigation, which may contribute to the way dreams often involve journeys through strange but semi-familiar spaces. The rhythmic coordination provided by theta activity may be what transforms random neural noise into the structured narratives we experience as dreams. Without this binding function, dreams might be merely disconnected flashes rather than the flowing stories we actually experience. Theta rhythms are the pulse that holds the dream together. Your brain paralyzes your body during REM sleep. During REM sleep, a remarkable safety mechanism takes effect. Your brain sends signals that paralyze nearly all your voluntary muscles. This phenomenon, called REM atonia, prevents you from physically acting out your dreams, protecting both you and anyone sleeping nearby from potential injury. Only the muscles that control breathing and eye movement are spared, which is why the eyes can still dart about beneath closed lids. The paralysis is so complete that even strong emotional responses in dreams, which would normally trigger movement, produce no physical action. This mechanism evolved because acting out the running, fighting, or falling common in dreams would be dangerous. The brain essentially disconnects the motor commands it generates during dreams from the muscles that would execute them. You may experience wild adventures in your dreams while lying almost perfectly still. Sleep paralysis occurs when awareness returns before the paralysis lifts. Sometimes the transition between sleep and waking goes wrong, and a person becomes conscious while their body is still paralyzed. This experience, called sleep paralysis, can be terrifying, as the person is fully aware but unable to move or speak. Episodes typically last from a few seconds to a couple of minutes, though they can feel much longer. Sleep paralysis is relatively common, with many people experiencing at least one episode during their lifetime. It is more likely to occur when sleep is disrupted, during periods of stress, or when sleeping on your back. While the experience is frightening, it is not dangerous and always resolves as the body catches up with the awakened mind. Understanding the mechanism behind sleep paralysis can make episodes easier to endure. Vivid hallucinations often accompany sleep paralysis episodes. People experiencing sleep paralysis frequently report hallucinations that blend dream imagery with the waking environment. These hallucinations often involve a sense of presence, as though someone or something is in the room, and may include visual, auditory, or tactile perceptions. Common experiences include seeing shadowy figures, hearing breathing or footsteps, or feeling pressure on the chest. These hallucinations occur because the brain is still in a dreamlike state, while conscious perception of the real environment is returning. Throughout history, sleep paralysis hallucinations have likely inspired stories of demons, ghosts, and alien abductions. The terrifying quality of these episodes comes from the combination of helplessness and intrusive, often threatening imagery. Knowing that these experiences are ordinary products of a brain caught between sleep and waking can reduce their power. REM atonia is controlled by brainstem and spinal circuits. The paralysis of REM sleep originates from specific circuits in the brainstem and spinal cord that actively inhibit motor neurons. A region of the brainstem called the sublaterodorsal nucleus plays a key role in triggering this inhibition during REM sleep. Signals from this region activate neurons in the spinal cord that release inhibitory neurotransmitters onto the motor neurons controlling skeletal muscles. This is not simply an absence of movement commands, but an active suppression of the ability to move. When these circuits fail to function properly, the result can be REM sleep behavior disorder, in which people physically act out their dreams. Understanding the neural basis of REM atonia has helped explain various sleep disorders and opened potential therapeutic avenues. The paralysis system is a sophisticated piece of evolutionary engineering. Tiny twitches sometimes leak through the paralysis as fragments of motion. Despite the normally complete paralysis of REM sleep, small twitches sometimes escape, causing brief jerks of the fingers, face, or limbs. These twitches may represent fragments of dream movements that momentarily overcome the inhibition. Watching a sleeping person during REM sleep, you might notice slight movements of the eyes, lips, or fingers that hint at the dream action occurring within. The twitches are normal and do not indicate that the paralysis system is failing. They represent the imperfect nature of any biological system being briefly overwhelmed by particularly strong dream commands. In some animals, these twitches are thought to play a role in brain development, helping to calibrate the motor system. These tiny leaks of movement are like crackling static, breaking through an otherwise silent radio. Hypnagogic flashes bloom right as you fall asleep. The transition from waking to sleep is marked by a fascinating intermediate state called hypnagogia, during which vivid images, sounds, and sensations can appear spontaneously. These hypnagogic experiences often include geometric patterns, floating shapes, faces, or brief scenes that seem to emerge from nowhere. Unlike full dreams, hypnagogic imagery is typically fragmentary and disconnected, lasting only seconds before consciousness fades entirely. Many creative thinkers have deliberately cultivated this state, finding that the freed associations of hypnagogia can produce novel ideas. The experiences can be so vivid that people sometimes jerk awake, startled by an image or sound that felt entirely real. Hypnagogia represents the brain's gradual shift from processing external reality to generating its own internal experience. This doorway between waking and sleeping is a unique window into how consciousness transitions between states. Hypnopompic echoes linger as you wake from dreams. Just as there is a threshold state entering sleep, there is a corresponding twilight state upon awakening called hypnopompia. During this period, dream imagery and sensations can persist, even as awareness of the waking world returns. People sometimes report seeing dream figures in their bedroom or hearing sounds from their dreams continuing into waking. The hypnopompic state can create momentary confusion about what is real and what was dreamed. Like hypnagogic experiences, hypnopompic phenomena can include hallucinations of voices, music, or visual patterns. These experiences are generally brief and harmless, resolving as the brain completes its transition to full wakefulness. The lingering of dream traces into waking shows how gradually the brain separates its internal world from external reality. Exploding head syndrome blasts imaginary sounds at sleep onset. Despite its alarming name, exploding head syndrome is a harmless sleep phenomenon in which a person hears a loud noise, like a gunshot, explosion, or cymbal crash, just as they are falling asleep. The sound exists only in the mind, but can be startlingly loud and is often accompanied by a flash of perceived light. The experience typically lasts only a moment and causes no pain, though it can be frightening for those who do not understand what is happening. The exact cause is unknown, but it may involve a glitch in the process by which the brain normally shuts down sensory processing as sleep begins. Episodes can occur in clusters during periods of stress or disrupted sleep. Once people understand that the syndrome is harmless and relatively common, the fear associated with episodes often diminishes. The dramatic name captures the intensity of an experience that is actually quite benign. False awakenings can create dream-within-dream loops. Sometimes dreamers will dream that they have woken up, only to discover that this awakening was itself part of the dream. These false awakenings can occur multiple times in sequence, creating nested layers of seeming reality that only resolve when true waking finally occurs. During a false awakening, the dreamer typically goes through normal morning routines like getting out of bed, checking the time, or starting to dress, before something strange reveals that the experience is still a dream. The phenomenon demonstrates how convincingly the brain can simulate the experience of waking reality even while remaining asleep. False awakenings are associated with lucid dreaming and can sometimes be used as a trigger for becoming lucid. The experience of multiple false awakenings can be disorienting but is not harmful. They are reminders that our perception of reality, even our perception of being awake, is a construction of the brain. Time inside dreams can stretch or compress, strangely. The subjective experience of time during dreams does not always match the objective duration of REM sleep. Some dreams seem to span hours or even days, while only minutes have passed on the clock. Conversely, long REM periods sometimes produce dreams that feel brief and compact. Research on this question has produced mixed results, with some studies suggesting that dream time roughly matches real time, and others finding significant distortions. The brain's timekeeping mechanisms operate differently during sleep, which may contribute to these subjective variations. Lucid dreamers who have tried to time activities within dreams report inconsistent results. Whether time truly stretches in dreams or merely seems to upon recall remains an open question. The elastic quality of dream time is part of what makes dreams feel so different from waking experience. People born blind dream in sound, touch, and smell. Those who have been blind from birth never experience visual imagery in their dreams, since they have no visual memories or concepts to draw upon. Instead, their dreams unfold through the other senses: sound, touch, smell, taste, and spatial awareness. Research shows that blind dreamers report rich auditory experiences, tactile sensations, and emotional content that is just as vivid as sighted people's visual dreams. People who lost their sight later in life may still dream visually, drawing on memories from their sighted years. The dreams of congenitally blind individuals demonstrate that dreaming is not fundamentally about images, but about the brain simulating experience through whatever sensory channels are available. These findings reveal the flexibility of the dreaming brain to create immersive inner worlds regardless of which senses dominate. Dreams adapt to the sensory hardware each brain has learned to use. Most dreams are in color, despite old black and white reports. Contemporary dream research has established that the vast majority of dreams occur in color, not in black and white as some older surveys suggested. The earlier findings may have been influenced by the prevalence of black and white film and television, which led people to describe their dreams in those terms. When researchers began asking more specific questions about color in dreams, reports of color content increased dramatically. Brain imaging confirms that visual cortex areas responsible for color processing are active during REM sleep. Occasionally, people do report dreams with muted or absent color, but this is the exception rather than the rule. Some dreams feature colors more vivid and saturated than anything in real life. The colorful nature of dreams speaks to how fully the visual brain engages during sleep. Tastes and smells appear rarely but still shape dream emotions. Olfactory and gustatory experiences are among the least commonly reported sensory elements in dreams, yet when they do occur, they can powerfully influence dream mood. The scent of a familiar place or person can evoke strong emotions within the dream, even if the smell is not consciously noted. Taste experiences tend to appear in dreams involving eating or drinking, often tied to pleasurable or disgusting emotional tones. The relative rarity of these chemical senses in dream reports may reflect the difficulty of articulating smell and taste memories rather than their true absence. The olfactory cortex has direct connections to emotional and memory centers of the brain, which explains the potent emotional impact when smells do appear. Even infrequent, these sensory appearances contribute meaningfully to the texture of dream experience. Dreams can thus engage every avenue of sense, even if not equally. Pain shows up less often and usually feels muted in dreams. Pain does appear in dreams, but it is relatively uncommon and typically less intense than waking pain. Some dreamers report sharp pain experiences in nightmares or anxiety dreams, while others describe aches or discomfort that influence dream events. The dampening of pain sensation during sleep may be related to changes in pain processing circuits that occur as part of the general inhibition of the body. The brain can represent the expectation of pain, such as anticipating an injury in a dream, without generating the full sensory experience. People who suffer from chronic pain sometimes incorporate their pain into dreams, though the experience may be transformed or symbolized. When pain does appear intensely in dreams, it can be disturbing and memorable. Overall, dreams tend to spare us from the full force of painful sensations. Eye movements sometimes mirror where dreamers look inside dreams. The rapid eye movements that characterize REM sleep are not random, but may correspond to where the dreamer is looking within the dream. Studies of lucid dreamers instructed to make deliberate eye movements while dreaming have shown that these internal gaze shifts match recorded eye movements on polysomnography. This suggests that eye movement circuits remain active and coordinated with the imagined visual experience of dreams. Not all dreams involve extensive visual exploration, so the correspondence is not perfect. Nevertheless, the link between dream gaze and actual eye movement supports the idea that dreaming involves genuine perceptual simulation. It also provides researchers with a physiological window into dream content. The eyes, in a sense, trace the scenery of the dream world. Motor cortex activates for actions your body does not make. When dreamers imagine performing actions like walking, running, or reaching, the motor cortex fires in patterns similar to those seen during actual movement. This activation reveals that dreaming involves more than passive imagery. The brain genuinely commands actions, even though those commands do not reach the muscles due to REM atonia. Studies using brain imaging have confirmed motor cortex involvement during dreams involving physical activity. In some cases, supplementary motor areas and premotor cortex also become active. This internal rehearsal of movement may play a role in motor learning and memory consolidation. It demonstrates that dreams engage the brain nearly as fully as waking action, producing experience from within rather than from without. The sleeping body lies still while the dreaming brain runs through the motions. External sounds weave themselves into dream storylines. Sounds from the sleeper's environment can slip into dreams, becoming incorporated into the dream narrative in transformed ways. An alarm clock might become a ringing telephone, a barking dog might appear as a warning shout, or traffic noise might become part of a busy dream scene. This phenomenon demonstrates that the sleeping brain remains partially in contact with the outside world, processing incoming sounds even while generating internal experience. The degree to which external sounds are incorporated depends on their intensity and personal significance. A parent may be more easily roused by their child's cry than by equally loud random noise. The blending of external and internal experience in dreams illustrates the brain's remarkable ability to integrate new information into ongoing narratives. Dreams are porous membranes through which outside reality sometimes leaks. Light flashes can appear as lightning or camera flashes in dreams. Visual stimuli applied during REM sleep can also influence dream content, though the sleeping eyelids filter most light. When light does penetrate, it may be perceived within the dream as lightning, an explosion, a camera flash, or a bright sun appearing suddenly. Experiments stimulating sleepers with light have found that such experiences are woven into dream scenarios in contextually appropriate ways. This suggests that the dreaming brain seeks to make sense of incoming information by incorporating it into its ongoing story. The phenomenon is similar to how the brain incorporates tactile stimuli, like a blanket slipping off into a dream of suddenly feeling cold. Light integration shows that even during the deepest stages of dreaming, the brain remains capable of responding to the environment. External reality gently knocks at the door of dreams. Your own name still cuts through from the outside world. The brain remains selectively alert to meaningful stimuli even during sleep, and one of the most significant of these is one's own name. Studies have shown that sleeping individuals are more likely to respond to their own name than to other names or words. This phenomenon relates to the cocktail party effect, the ability to notice personally relevant information, even when attention is focused elsewhere. During sleep, the brain's screening mechanisms allow certain high-priority signals to break through the barrier of sleep. This partial vigilance may have evolutionary value, allowing more rapid arousal to meaningful calls. If a name is heard during REM sleep, it sometimes enters the dream content before causing awakening. The sleeping brain is thus not entirely cut off from the world, but remains ready to respond if needed. A gentle tap can appear as a door knock in your dream. Tactile stimulation during sleep is frequently incorporated into dreams, with light touches becoming dream elements that fit the narrative context. A gentle tap on the shoulder might become part of a dream in which someone is trying to get your attention. Pressure from a twisted blanket might appear as being constrained or held. These incorporations typically happen without awakening the sleeper, as the dream brain finds a way to explain the sensation. The phenomenon has been documented experimentally, with researchers applying mild stimuli and then awakening subjects to collect dream reports. The seamless integration of external touch into dreams demonstrates the narrative creativity of the sleeping brain. Physical sensations become characters and events in the dream's ongoing story. An alarm clock often morphs into a phone ringing in dreams. The classic example of sound incorporation is the alarm clock that becomes part of the dream before finally waking the sleeper. Many people have experienced dreaming of a phone ringing, a doorbell sounding, or a fire alarm blaring, only to wake and realize the sound was their morning alarm. This transformation occurs because the dreaming brain attempts to maintain sleep by explaining away intrusions. If a narrative explanation succeeds, sleep may continue. If it fails, awakening occurs. The specific transformation often reflects what would make sense within the dream scenario at that moment. This creative reinterpreting sometimes buys several extra minutes of sleep, as the dream finds ways to incorporate the sound. The flexibility of dream storylines allows almost any sound to find a place within them. Slow waves gate which outside cues get woven into dreams. The incorporation of external stimuli into dreams depends partly on the phase of sleep oscillation occurring when the stimulus arrives. During certain phases of slow-wave activity, the brain is more blocked from external input, while during other phases it is more receptive. Researchers have demonstrated that stimuli timed to specific phases of sleep oscillations are more or less likely to be incorporated into dream content. This gating mechanism explains why incorporation is inconsistent and unpredictable. The brain's rhythmic activity acts as a filter, alternately opening and closing windows to the outside world. Understanding this gating has implications for targeted memory reactivation during sleep. The ebb and flow of brainwaves determines how permeable the dream barrier is at any given moment. The scent of roses can make a nightmare gentler. A remarkable experiment demonstrated that introducing the scent of roses during REM sleep could make dreams more pleasant. Subjects exposed to the smell of roses while dreaming reported more positive dream content and emotional tone. This suggests that olfactory stimuli bypass conscious awareness and directly influence the emotional flavor of dreams. The effect occurs without the smell necessarily appearing as a dream element. Instead, the mood shifts subtly. Unpleasant odors, conversely, can introduce negative emotions and darker dream themes. This finding opens possibilities for therapeutic manipulation of dream experience. A simple fragrance wafting through the bedroom might shape the night's inner journey in quiet but meaningful ways. Smells nudge dream mood without appearing as smells themselves. When scents influence dreams, they typically do so through emotion, rather than direct representation. Dreamers rarely report consciously smelling the introduced odor. Rather, they experience a shift in the dream's atmosphere. A pleasant scent might make dream settings seem friendlier and interactions more positive. An unpleasant smell might introduce threatening overtones or uncomfortable scenarios. This indirect influence reflects the close anatomical connection between the olfactory system and the limbic brain regions that regulate emotion. The nose speaks to the emotional brain in a language below conscious awareness. Dreams are thus shaped by sensory channels we are not even aware of using. Pleasant scents introduced during sleep soften dream tone. The systematic use of pleasant odors during sleep has been shown to reduce the incidence of negative dream content. This softening effect has potential applications for people who suffer from frequent nightmares or disturbing dreams. Aromatherapy already uses scent for relaxation and mood enhancement, and its extension into sleep represents a natural development. The mechanism appears to involve olfactory stimulation of the amygdala and limbic system during REM sleep. These effects are modest and do not guarantee pleasant dreams, but they tilt the odds toward more agreeable experiences. The therapeutic potential of dream scent manipulation is still being explored. Gentle fragrances may become a tool for cultivating better nights. The olfactory system connects directly to emotional brain regions. Unlike other senses, which relay through the thalamus on the way to the cortex, the olfactory system has direct projections to the amygdala and hippocampus. This anatomical shortcut explains why smells can trigger powerful emotional reactions and vivid memories. When odors reach the brain during sleep, they bypass the usual sensory gating and speak directly to emotional centers. This direct pathway underlies the ability of scent to influence dream mood without conscious detection. The ancient nature of the olfactory system, predating later developments in visual and auditory processing, explains its intimate link to emotion. Smells carry an emotional charge that other senses often lack. In dreams, this emotional potency operates behind the scenes, coloring experience invisibly. Day residue shows up in dreams with a quirky delay. Events from the previous day often appear in our dreams, a phenomenon known as day residue. However, the appearance is usually not straightforward. Fragments of the day's experiences are woven into new contexts and narratives. Research has shown that memories can take several days to appear in dreams, with a peak around the 5th to 7th night after an event. This delay suggests that dreams are involved in the gradual process of consolidating and integrating new memories into long-term storage. The transformation of day residue into dream content often obscures its source, making connections to waking events difficult to recognize. Events that were emotionally significant or personally relevant are more likely to appear. Day residue reveals that dreams draw on recent experience even as they transform it beyond easy recognition. Dreams remix fragments of life into entirely new scenes. The dream brain does not simply replay memories, but creatively recombines elements from different experiences. A location from one memory may combine with people from another, and an emotional tone from a third. This remixing may serve to integrate new learning with existing knowledge, finding unexpected connections. The result is dream scenes that feel familiar yet are entirely novel constructions. This creative synthesis may underlie some of the problem-solving insights that occasionally occur in dreams. The fragmentary nature of dream content reflects the brain's effort to consolidate and cross-reference diverse experiences. Dreams are the brain's nightly editing room, splicing together footage from countless sources. The hippocampus replays daytime routes during sleep. During sleep, the hippocampus exhibits replay activity, in which patterns of neural firing from the day are reactivated in compressed form. This replay has been observed most clearly for spatial navigation tasks, where sequences of place cell activations repeat during sleep. The replay is thought to help consolidate spatial memories and transfer them to long-term cortical storage. Similar replay has been observed for other types of learning as well. The timing of replay often occurs during slow-wave sleep, though REM sleep also contributes to memory consolidation. Hippocampal replay demonstrates that the sleeping brain is actively processing the day's experiences. The neural echoes of the day reverberate through the sleeping brain. A sound played during sleep can strengthen a chosen memory. Targeted memory reactivation is a technique in which cues associated with a specific learning experience are presented during sleep. If a sound or smell was present during learning, playing that cue during sleep can selectively strengthen the associated memory. This technique has been used to enhance performance on spatial memory tasks, vocabulary learning, and skill acquisition. The cue is believed to trigger replay of the associated memory network during sleep. The method can be applied without disrupting sleep if cues are gentle enough. Targeted memory reactivation represents a promising approach for optimizing learning. What we hear in the night can shape what we remember in the morning. Targeted memory reactivation strengthens chosen memories overnight. Beyond simple cueing, researchers have explored protocols for using targeted memory reactivation to prioritize certain memories over others. By selectively presenting cues for some learned material, but not others, the associated memories show enhanced retention. This finding confirms that sleep-dependent memory consolidation is influenced by external input. The principle opens possibilities for educational and clinical applications. Patients might use cueing to strengthen therapeutic learning, or students might reinforce study material. Care must be taken to avoid disrupting the natural architecture of sleep. Targeted reactivation shows that sleep is not a passive time but an opportunity for guided memory enhancement. Learning before bed makes related dreams more likely. What we study or experience in the hours before sleep influences what we dream about. Intensive learning tasks increase the probability of dreams that incorporate elements of the learned material. This relationship between pre-sleep learning and dream content supports the hypothesis that dreams participate in memory processing. Dreams about recently learned material have been associated with improved performance the next day. The content need not be a direct representation. Symbolic or transformed versions of the material may appear. This finding has implications for timing study and practice sessions relative to sleep. The final hours of the day prime the dream stage for the night's performance. Threat simulations often play out safely in dreams. The threat simulation theory proposes that one function of dreaming is to rehearse responses to dangerous situations in a safe neurobiological environment. Dreams frequently contain threats such as being chased, attacked, or caught in dangerous situations. In these dreams, we practice fleeing, hiding, fighting, or finding solutions without facing real physical consequences. Rehearsing these responses may improve our ability to react appropriately if similar situations occur in waking life. The theory explains why negative dream content is so prevalent across cultures. The emotional intensity of threat dreams ensures that the rehearsal is taken seriously by the brain. Dreams may be a nightly training ground for survival. Social worlds get rehearsed at night like practice runs. Social simulation theory extends the threat simulation idea to encompass social interactions as well. Many dreams involve complex social situations such as conversations, conflicts, romantic encounters, or navigating group dynamics. These dreams may help us practice interpreting social cues, managing relationships, and predicting others' behavior. The social worlds of dreams often feature people we know, allowing us to rehearse interactions that might occur in waking life. Mistakes made in dream interactions carry no social cost, allowing experimentation and learning. The prevalence of social content in dreams suggests that relationship maintenance is a core function of dream activity. Night after night, we practice being social creatures. Most dream characters are familiar faces rather than strangers. Studies of dream content have found that the majority of people appearing in dreams are known to the dreamer in some way. Family members, friends, co-workers, and acquaintances populate our dreams far more than complete strangers. When strangers do appear, they often have some recognizable social role or function. This familiarity bias supports the idea that dreams simulate and rehearse our existing social networks. The emotional significance of relationships may determine their likelihood of appearing in dreams. Known characters may be easier for the brain to simulate convincingly than novel ones. Our dreamcasts are largely drawn from the roster of our waking social lives. Dreams may help us practice navigating relationships. By simulating social scenarios, dreams may provide a form of relationship practice that prepares us for waking interactions. Dreams can present conflicts, reconciliations, misunderstandings, and intimate moments that mirror real-life relationship challenges. Emotions experienced in these dream interactions can feel genuine and may influence how we perceive relationships upon waking. Some researchers suggest that dreams help process unresolved relationship issues or anticipate future social situations. The rehearsal aspect may be unconscious, but could still confer benefits in social cognition. Navigating complex social worlds is a demanding cognitive task that dreams may help support. Every night offers a social rehearsal with an infinite cast and endless scenarios. Threatening scenarios in dreams often end with escape or resolution. Although threat dreams can be intensely frightening during the experience, they frequently conclude with the dreamer escaping, overcoming, or otherwise resolving the threat. Rarely do dreamers remain trapped indefinitely or experience the full consequences of a threat. This pattern supports the idea that threat dreams function as rehearsal rather than random horror. Successfully navigating dream threats may build a sense of coping ability that carries into waking life. Dreams may generate challenges calibrated to our perceived ability to manage them. The resolution of threat scenarios may be part of how dreams contribute to emotional regulation. Even in the darkest dream, there is often a way out. Nightmare frequency rises with stress, then falls when stress eases. Nightmares are not random occurrences, but are closely linked to our emotional state. Periods of heightened stress, anxiety, or trauma reliably increase the frequency and intensity of nightmares. When stresses are resolved or diminished, nightmare frequency tends to decrease correspondingly. This relationship suggests that nightmares may be part of the mind's attempt to process and cope with difficult emotions. Chronic stress that does not resolve can lead to persistent nightmare problems that may require intervention. Some people are more prone to nightmares than others, with personality traits like neuroticism and thin boundaries influencing vulnerability. Understanding the stress-nightmare connection can help people interpret their nightmare experiences as signals from the mind rather than meaningless terrors. Nightmares can be treated without medication in many cases. Effective psychological treatments for chronic nightmares exist and can provide relief without the side effects of medication. Cognitive behavioral approaches, including exposure therapy and imagery training, have strong evidence for reducing nightmare frequency and distress. These treatments address the underlying cognitive and emotional patterns that feed recurrent nightmares. Treatment often involves learning to view nightmares differently, reducing their power to disturb. For many people, a few sessions of targeted therapy can produce lasting improvement. Medication remains an option for severe cases, but is rarely necessary for most nightmare sufferers. Non-pharmacological approaches offer hope for those whose sleep is haunted by unwanted dreams. Imagery rehearsal therapy lets you rewrite a nightmare's ending. Imagery rehearsal therapy is a specific technique in which sufferers mentally rehearse a new, less distressing version of a recurrent nightmare while awake. The process involves writing down the nightmare, changing the script to include a more positive or neutral resolution, and then vividly imagining the new version repeatedly. Over time, this rehearsal can replace the old nightmare pattern with the new, more benign version. Studies have shown significant reductions in nightmare frequency and intensity using this method. The technique empowers dreamers by giving them a sense of control over their dream life. Imagery rehearsal does not require remembering the dream in full detail, and works even when the nightmare content is vague. Rewriting the nightmare is a form of therapeutic creativity. Recurrent dreams often resolve when their waking trigger changes. Many people experience the same dream or nightmare repeatedly, over months or years. These recurrent dreams are often linked to unresolved waking issues, concerns, or emotional conflicts. When the triggering issue is addressed, or the emotional conflict is resolved, recurrent dreams frequently cease on their own. This pattern supports the idea that recurring dreams are the mind's way of continuously processing an unresolved matter. Some recurrent dreams shift gradually over time, evolving as the dreamer's waking situation changes. Identifying the waking trigger can provide insight into what the dream is attempting to process. Recurrent dreams may be persistent invitations from the unconscious to pay attention to something important. PTSD can fill sleep with recurring emotionally loaded dreams. Post-traumatic stress disorder often includes intrusive nightmares that replay or reference the traumatic event. These nightmares can be so distressing that people with PTSD develop anxiety about sleep itself, leading to insomnia. The dreams may feature exact replays of trauma or symbolic representations that carry the same emotional charge. REM sleep in PTSD may fail to perform its normal function of processing and neutralizing emotional memories. Treatment approaches for trauma-related nightmares often include elements of exposure therapy alongside other PTSD interventions. The persistence of traumatic nightmares reflects how deeply extreme experiences can embed themselves in the sleeping mind. Healing from trauma often involves making peace with the night. Nightmare therapies can reduce distress and improve sleep quality. Successful treatment of chronic nightmares yields benefits beyond just stopping bad dreams. People who undergo nightmare therapy often report improved overall sleep quality, including longer and deeper sleep. Reduced dread of sleep improves nightly routines and helps establish healthy sleep patterns. The emotional relief from escaping recurrent nightmares can have positive effects on daytime mood and functioning. Treat nightmares successfully, and the benefits ripple outward into many aspects of life. The investment in nightmare therapy is one of the most efficient interventions in sleep medicine. Few treatments offer such a favorable ratio of effort to benefit. Teeth falling and flying are common themes across many cultures. Certain dream themes appear with remarkable consistency across different cultures and historical periods. Dreams of teeth falling out are among the most frequently reported and have been documented as far back as ancient Greece. Flying dreams are similarly universal, appearing in dream reports from cultures around the world. Falling, being chased, appearing naked in public, and taking exams are also common themes. The universality of these themes suggests that they may reflect shared human concerns or biological processes. Cultural interpretation of these dreams varies widely, but the dreams themselves transcend cultural boundaries. The commonality of dream themes points to the deep similarities in human psychology. Flying dreams often bring feelings of freedom and joy. Among all dream themes, flying is perhaps the most positively experienced. Dreamers frequently describe exhilarating sensations of freedom, power, and joy while flying in dreams. The experience ranges from gliding just above the ground to soaring high above landscapes. Sometimes flight requires effort or techniques within the dream, while other times it happens effortlessly. Flying dreams are often associated with feelings of transcendence and escape from limitations. Some people learn to induce flying in lucid dreams, deliberately seeking out this pleasurable experience. The feeling of flight is so compelling that many waking inventions have been motivated by the desire to recreate it. Dreams offer the flight that physics denies. People rarely write or read text cleanly in dreams. A curious feature of dreams is the difficulty of processing written language within them. When dreamers try to read text in dreams, the words often blur, shift, or fail to make sense. Writing similarly tends to come out garbled or illegible upon inspection. This difficulty is believed to relate to the reduced activity of language processing regions during REM sleep. The instability of text in dreams is sometimes used as a reality check in lucid dreaming training. If text changes upon rereading, the reader may realize they are dreaming. The absence of stable text in dreams contrasts with how easily the brain generates visual imagery in conversation. Written language is a relatively recent invention that the dreaming brain has not fully incorporated. Mirrors and faces often warp as the brain's self-model becomes unstable. Looking in mirrors during dreams can produce disturbing results, as the reflected image often appears distorted, aged, or unfamiliar. Faces in dreams, including one's own, may shift, blur, or take on strange characteristics. These distortions are thought to reflect the instability of the brain's self-model during dreaming. The neural systems that maintain our sense of identity and body image operate differently during REM sleep. Mirror distortions are another common reality check for those training in lucid dreaming. Seeing an unfamiliar face in the mirror can prompt the realization that one is dreaming. The unstable self-image of dreams points to how constructed and context-dependent our sense of self truly is. Out-of-body sensations can arise from REM intrusions. The sensation of floating outside one's body, or viewing oneself from above, has a neurological basis linked to REM sleep. When elements of REM sleep intrude into waking consciousness, or when vestibular processing becomes disrupted, out-of-body experiences can occur. These experiences share features with certain dream states, particularly lucid dreams with unusual perspectives. The same brain regions involved in spatial orientation and body maps are implicated in both dreams and out-of-body experiences. For centuries, these experiences were interpreted as supernatural, but neuroscience now understands them as products of brain processes. Deliberate induction of out-of-body states is a goal of some lucid dreaming practitioners. The floating sensation feels uncanny, but it originates within the confines of the skull. Scientists have had two-way conversations with lucid dreamers. One of the most remarkable achievements in dream research is the establishment of two-way communication with people while they are dreaming. Lucid dreamers, aware they are dreaming, can signal to researchers using prearranged eye movements or muscle twitches. Researchers have also successfully sent questions to dreamers using sounds, lights, or electrical stimulation, and received responses in real time. This communication has allowed direct investigation of dream content and mental operations during the dream itself. The breakthrough has transformed what can be studied about dreams, moving beyond reliance on imperfect after-waking reports. Two-way communication opens the possibility of guiding dream experiences for therapeutic or experimental purposes. The sleeping mind is more accessible than ever before. In lucid dreams, people have solved problems and signaled answers. Lucid dreamers have demonstrated that cognitive abilities remain active during dreams by solving problems and indicating answers through eye movements. In experiments, lucid dreamers have performed mathematical calculations, followed instructions, and responded to questions while fully immersed in the dream state. These findings prove that dreaming involves genuine cognition, not just passive reception of images. The level of cognitive control varies between individuals and improves with practice. Some researchers are exploring whether lucid dreaming can be used to practice skills or work through problems. The active engagement of the lucid dreamer contrasts with the passive experiencing of ordinary dreams. Mind remains potent even within the dream state. Lucid dreams are more likely in late-night REM periods. The probability of experiencing a lucid dream is not uniform across the night, but increases during the later REM periods that occur in the early morning. These later REM periods are longer and involve more intense brain activity, conditions that favor self-awareness within dreams. Waking briefly during the early morning hours and then returning to sleep increases the chances of lucidity. This pattern is exploited by lucid dreaming techniques that involve interrupted sleep, followed by return to rest. Understanding the natural rhythm of REM increases the effectiveness of lucid dreaming training. The final hours of sleep are the prime territory for lucid awareness. Late risers have more opportunities for conscious dreaming. Reality checks by day can carry into dream awareness. One proven method for inducing lucid dreams involves habitually questioning reality during waking life. By regularly asking whether one is dreaming and checking environmental indicators, this habit can become automatic enough to occur during dreams. Common reality checks include trying to push a finger through the palm or rereading text that may change in dreams. When these checks are performed in dreams, the unusual results can trigger lucid awareness. The method relies on the continuation of habitual patterns from waking life into sleep. Regular practice throughout the day builds the automatic questioning that can unlock dream lucidity. Daily habits train the dreaming mind. Once lucid, dream control becomes easier with practice. Achieving lucidity is only the first step. Learning to maintain and deepen awareness while controlling dream content is a skill that develops over time. Novice lucid dreamers often wake up quickly or lose lucidity as excitement overwhelms their calm. With practice, dreamers learn to stabilize the dream state, extend lucid episodes, and direct dream content deliberately. Techniques like spinning, rubbing hands, or demanding clarity help maintain the dream. Control over dream content ranges from changing scenes to summoning characters or flight. Some lucid dreamers develop remarkable abilities to shape their inner worlds. Mastery of lucid dreaming is an acquired art. The MELD technique primes the mind to notice dreaming. Mnemonic induction of lucid dreams, or MILD, is one of the most widely used and studied techniques for inducing lucid dreams. The method involves setting a strong intention to recognize that you are dreaming the next time you enter a dream. This intention is typically rehearsed mentally while falling asleep, or after waking briefly in the night. MILD works by leveraging prospective memory, the ability to remember to do something in the future. Successful MILD practice involves vivid visualization of becoming lucid in a dream and repeating affirmations of the intention. The technique requires no special equipment and can be learned by anyone with sufficient motivation. MILD trains the sleeping mind to carry waking intentions into the dream state. WBTB timing catches REM surges and boosts lucidity. Wake Back to Bed, or WBTB, is a technique that exploits the natural architecture of sleep to increase lucid dreaming chances. The sleeper sets an alarm to wake after 5 or 6 hours of sleep, stays awake briefly, and then returns to sleep. Since REM periods become longer and more frequent toward morning, this timing catches the brain as it re-enters REM-rich sleep. WBTB is often combined with other techniques like MILD for maximum effect. The brief period of wakefulness primes the mind for awareness, while the return to sleep provides access to dreaming. Research has confirmed that WBTB significantly increases lucid dream frequency. Strategic interruption of sleep can unlock conscious dreaming. SSILD cycles the senses to spark lucidity. Senses-initiated lucid dreaming, or SSILD, is a relatively newer technique that focuses on cycling attention through different sensory modalities while falling asleep. The practitioner alternates attention between visual impressions behind the eyes, sounds in the environment, and bodily sensations. This cycling is repeated several times with relaxed, passive attention. The technique is believed to heighten awareness of the sleep onset process and increase the chance of noticing when dreaming begins. SSILD does not require strong concentration and is often described as easy to learn. Many practitioners report hypnagogic experiences and lucid dreams after consistent practice. Sensory cycling attunes the mind to the threshold of dreams. Galantamine can dramatically raise lucid dream success rates. Galantamine is a cholinesterase inhibitor that increases the neurotransmitter acetylcholine, which plays a key role in REM sleep. When taken strategically in the middle of the night with a WBTB protocol, galantamine significantly increases the probability of experiencing lucid dreams. Studies have shown that galantamine combined with MILD and WBTB produces lucid dream rates far exceeding placebo conditions. The substance does not induce dreams directly, but enhances the conditions under which lucidity naturally arises. Users should be informed about potential side effects and contraindications. Galantamine represents one of the most effective pharmacological aids for lucid dream induction. Chemistry can assist the pursuit of conscious dreaming. Rehearsing skills in lucid dreams can feel strikingly real. The vividness of lucid dreams allows for practice of skills that feels remarkably similar to waking practice. Athletes, musicians, and others have used lucid dreams to rehearse motor skills, visualize performances, and prepare for challenges. The motor cortex activation during dreamed actions may contribute to the training effect. While dream practice cannot fully replace physical practice, it can complement and enhance learning. The emotional stakes of performing in dreams feel real, adding another dimension to the rehearsal. Some practitioners use lucid dreams to overcome fears or practice speeches. The lucid dream state is a private virtual reality studio for the mind. Lucid dreamers can dampen nightmares from within the dream. One of the practical applications of lucid dreaming is the ability to confront and defuse nightmares while they are occurring. Once aware they are dreaming, lucid dreamers can choose to face nightmare figures, transform the scenario, or simply will themselves to wake. This in-dream intervention can reduce the distress of recurrent nightmares and restore a sense of control over one's sleep. The approach complements waking therapeutic techniques for nightmare management. Lucid nightmare intervention is particularly valuable for those with frequent or severe nightmares. Teaching lucid dreaming skills to nightmare sufferers has shown therapeutic benefits. Dreams need not be suffered passively, but can be engaged actively. Dream recall varies hugely between people and can be trained. Some people remember multiple dreams every night, while others claim never to dream at all. This variation in dream recall is not due to differences in actual dreaming, which is universal, but to differences in memory consolidation upon waking. People with higher dream recall tend to wake more frequently during or just after REM periods. Interest in dreams and attention to them upon waking also plays a role in how well they are remembered. Importantly, dream recall can be improved with deliberate practice and attention. Those who want to remember more dreams can train themselves to do so. Dream recall is a skill, not a fixed trait. Keeping a dream diary boosts recall within days. One of the most effective methods for improving dream recall is to keep a dream journal beside the bed. Upon waking, anything remembered about dreams is immediately written down, even if it is only a fragment or a feeling. This practice signals to the brain that dreams are important and worth remembering. Within days of starting a dream diary, most people notice an increase in the detail and frequency of their dream memories. Regular reviewing of the journal reinforces the habit and helps identify recurring themes or patterns. The act of writing encodes dream memories more firmly than mental rehearsal alone. A pen and notebook can open the door to the dream world. Nighttime awakenings catch more dreams than morning recall alone. Because dreams fade quickly from memory, catching them closer to when they occur improves recall. Setting alarms to wake at various points during the night allows dreamers to record fresh dream content. This technique is especially useful for capturing early night dreams that would otherwise be forgotten by morning. Multiple awakenings can yield a richer picture of the night's dream activity than relying solely on morning recall. The trade-off is disrupted sleep, so this approach is usually used for specific research or training purposes. For those serious about studying their own dreams, nighttime awakenings are a powerful tool. Brief interruption of sleep can yield rich harvests from the dream. Sleep inertia blurs dream memory within minutes of waking. The groggy state immediately after waking, known as sleep inertia, is a brief window during which dream memories are still accessible. As full waking consciousness returns, dream content rapidly fades and becomes harder to retrieve. The neurochemical shifts accompanying waking disrupt the maintenance of dream memories. For this reason, recording dreams must happen immediately, before even getting out of bed or checking the phone. Distractions during sleep inertia can cause an entire night's dreams to be lost. Respecting this fragile period is essential for anyone seeking to remember their dreams. The first moments of waking are precious for dream memory. A consistent wake time increases dream recall reliability. Having a regular wake time helps the brain anticipate the transition from sleep to waking, which can improve dream recall. Consistent sleep schedules lead to more predictable REM timing and more reliable access to late-morning REM dreams. Variable wake times disrupt circadian rhythms and can lead to missed opportunities for dream recall. People who wake at random times often have poorer dream memory than those with stable schedules. A set wake time also facilitates the use of techniques like WBTB that rely on timing relative to the sleep cycle. Sleep regularity supports not just health, but also access to the world of dreams. Routine is the friend of the dream rememberer. Sharing dreams with partners can increase emotional closeness. Discussing dreams with a partner or friend can enrich relationships by opening windows into each other's inner worlds. Sharing dreams invites vulnerability and can prompt conversations about fears, wishes, and memories that might not arise otherwise. Partners who share dreams often report feeling closer and more understood. The practice can also improve dream recall by making dream content socially relevant. Some cultures have traditions of dream sharing at the breakfast table or in groups. Dream sharing need not involve interpretation or analysis. Simply listening is valuable. Dreams can be bridges between separate minds. REM rebound after deprivation brings intense, frequent dreams. When REM sleep is suppressed for any period, the brain compensates with REM rebound once normal sleep resumes. During rebound, REM periods become longer and more frequent than usual. The dreams during REM rebound are often unusually vivid, emotionally intense, and memorable. This phenomenon has been documented in people recovering from sleep deprivation, illness, or withdrawal from REM-suppressing substances. REM rebound suggests that the brain has a need for REM sleep that it will fulfill when the opportunity arises. The intensity of rebound dreams can be disturbing or exhilarating depending on content. REM deprivation sets the stage for a surge of dreams once the debt is paid. Antidepressants can change dream vividness and frequency. Many antidepressant medications affect the neurotransmitter systems that regulate REM sleep. SSRIs and other common antidepressants often suppress REM sleep, leading to reduced dream recall while on the medication. When the medication is stopped, REM rebound can produce a wave of vivid, emotionally charged dreams. Some people report qualitative changes in dream content while on antidepressants, with dreams becoming more mundane or less memorable. Other medications, including some older tricyclic antidepressants, can increase dream vividness or nightmares. Understanding these effects can help patients anticipate changes in their dream lives when starting or stopping medication. Dreams are sensitive indicators of neurochemical shifts. Nicotine patches can make dreams unusually vivid. Nicotine replacement therapy, particularly patches worn overnight, is known for causing vivid and sometimes disturbing dreams. The nicotine absorbed during sleep stimulates acetylcholine receptors involved in REM sleep and dreaming. Users often report dreams that are more intense, bizarre, or emotionally charged than usual. Removing the patch before sleep can reduce these effects, though this may compromise the therapeutic purpose. The vivid dreams caused by nicotine patches are generally harmless, but can be disconcerting for those unprepared. This side effect is a reminder of how closely neurochemistry and dream experience are linked. A simple patch on the arm can transform the night's inner cinema. Alcohol suppresses early REM, then rebounds with heavy dreams. Alcohol consumed before sleep initially suppresses REM sleep during the early part of the night. As the alcohol is metabolized and its effects wear off, a REM rebound occurs in the second half of the night. This delayed surge of REM often produces vivid, fragmented, and sometimes disturbing dreams. The overall quality of sleep after drinking is compromised, with more awakenings and lighter sleep stages. People who drink regularly may experience chronic suppression of REM, followed by intense rebound when they abstain. The pattern contributes to the poor sleep quality associated with heavy alcohol use. Alcohol's relationship with dreams is one of delay, suppression, and compensatory surge. Cannabis can mute REM. Stopping can unleash vivid dreaming. Cannabis, particularly its main psychoactive component THC, reduces time spent in REM sleep. Regular cannabis users often report reduced dream recall, and some describe their sleep as dreamless. When cannabis use is stopped, a pronounced REM rebound occurs, often producing intensely vivid and sometimes unpleasant dreams. This rebound can last for days or weeks depending on the duration and intensity of prior use. The return of dreaming after cannabis cessation can be surprising for those who had forgotten what vivid dreams feel like. This effect is so predictable that it is used as a marker of brain recovery from cannabis. Dreams wait silently during use, then return in force when it ends. Beta blockers are notorious for causing strange dreams and nightmares. Beta-adrenergic blocking agents, used to treat high blood pressure and heart conditions, are well known for affecting sleep and dreams. Many users report vivid, bizarre, or disturbing dreams, including an increased frequency of nightmares. The mechanism may involve effects on norepinephrine signaling, which influences REM sleep and dream intensity. Not everyone on beta blockers experiences these effects, but they are common enough to be listed as a side effect. Switching to a different class of blood pressure medication can resolve the problem for those severely affected. The dream disturbances caused by beta blockers are a reminder of the brain's sensitivity to systemic medications. Pills taken for the heart can change what we see in sleep. Sleep apnea fragments REM and alters dream recall. Obstructive sleep apnea causes repeated interruptions of breathing during sleep, which fragment the normal sleep architecture. These disruptions often occur during REM sleep, cutting short periods of dreaming and reducing overall REM time. Many people with untreated apnea report poor dream recall or describe their sleep as dreamless. The frequent arousals may prevent the consolidation of dream memories that would normally occur during uninterrupted REM. The fragmented nature of sleep apnea nights means that dreams are often incomplete or forgotten. When apnea is treated successfully, patients sometimes report a resurgence of vivid dreaming. Sleep apnea steals not just restful sleep, but also the richness of dream life. Treating apnea can change dream patterns dramatically. When sleep apnea is treated with continuous positive airway pressure or other interventions, many patients experience a marked change in their dream lives. The restoration of uninterrupted REM sleep often leads to increased dream recall and more vivid dream content. Some patients experience intense dreams during the initial period of treatment, as the brain makes up for lost REM. This dream surge can include nightmares, positive dreams, or simply more remembered dreams than before. The change in dream patterns can be a positive indicator that treatment is working. For some, the return of dreaming is one of the most noticeable improvements from CPAP therapy. Treating the body allows the dreaming mind to flourish. Narcolepsy brings vivid dream intrusions at sleep onset. Narcolepsy is a sleep disorder characterized by disrupted regulation of sleep-wake states and REM sleep. People with narcolepsy often enter REM sleep almost immediately upon falling asleep, leading to vivid dream imagery at sleep onset. These hypnagogic hallucinations can be intense and may blend with waking perceptions in confusing ways. Sleep paralysis is also common in narcolepsy, trapping the person in a dreamlike state while awake. The boundary between waking and dreaming is unusually porous in narcolepsy, with dream elements intruding into waking life. Understanding narcolepsy has provided valuable insights into the mechanisms of REM sleep and dreaming. Narcolepsy is a condition where the dream world persistently leaks into waking. Cataplexy shows how emotion can trigger REM-like paralysis. Cataplexy is a symptom of narcolepsy in which strong emotions, often laughter or surprise, trigger sudden muscle weakness or paralysis. The mechanism is thought to involve intrusion of REM atonia, the paralysis normally confined to sleep, into waking consciousness. Episodes can range from mild weakness in the knees to complete collapse, lasting seconds to minutes. Cataplexy demonstrates how tightly REM mechanisms are linked to emotional systems in the brain. The triggering of paralysis by emotion rather than sleep illustrates the close connection between emotion and dream processes. Treatments for cataplexy often involve medications that affect REM sleep regulation. Cataplexy is the waking twin of the dream paralysis that protects sleepers. REM sleep behavior disorder plays dreams out in real life. REM sleep behavior disorder occurs when the normal paralysis of REM sleep fails, allowing people to physically act out their dreams. Sleepers may punch, kick, shout, or jump from bed while engaged in vivid dream scenarios. The movements often correspond to actions being performed in the dream, as confirmed by reports upon waking. Episodes can result in injury to the dreamer or their bed partner. The disorder is more common in older adults and is associated with certain neurodegenerative diseases. Medications can often reduce or eliminate episodes by restoring appropriate REM atonia. REM behavior disorder turns the dream stage into a physical arena. Acting out dreams can be an early sign of Parkinson's disease. REM sleep behavior disorder has emerged as an important early marker for neurodegenerative conditions, particularly Parkinson's disease and related disorders. In many cases, dream enactment behavior appears years or even decades before other symptoms of neurodegeneration become evident. The same brain regions that control REM atonia are affected by the pathology underlying Parkinson's. Recognizing REM behavior disorder opens a window for early intervention and monitoring. Not everyone with the disorder develops neurodegeneration, but the association is strong enough to warrant medical attention. Sleep researchers and neurologists are increasingly aware of this connection. The dreams we act out today may whisper warnings about the brain's tomorrow. Children dream differently, often with animals and simple adventures. The dreams of young children differ from adult dreams in several characteristic ways. Animals appear more frequently in children's dreams, often as principal characters or companions. Dream narratives tend to be simpler, with less complex social situations or abstract content. Children are less likely to appear as active participants in their own dreams, and may describe dreams in which they watch rather than act. Nightmares are common in early childhood, often featuring monsters, creatures, or separation from parents. As children mature, their dreams gradually come to resemble adult patterns in complexity and self-involvement. The dream life of childhood reflects both the developing brain and the child's limited life experience. Adolescents report more intense and socially charged dreams. During adolescence, dreams shift toward greater emotional intensity and social content. Dreams often feature peers, romantic interests, and themes of identity and belonging. The hormonal and neurological changes of puberty likely contribute to these shifts in dream content. Adolescents may also report more vivid and memorable dreams as REM sleep patterns change. Social anxieties, identity questions, and the emotional turbulence of teenage years find expression in dream narratives. The heightened emotionality of adolescent dreams mirrors the emotional volatility of waking adolescent life. Dreams during these years are a reflection of the transformative inner work of becoming an adult. Older adults recall fewer dreams but still have REM sleep. Dream recall tends to decline in older adulthood, with many elderly individuals reporting that they rarely remember dreaming. This decline in recall does not mean that dreaming has ceased. Polysomnography shows that older adults continue to experience REM sleep. The reduction in recall may relate to changes in sleep architecture, fewer awakenings during REM, or changes in memory consolidation. Some studies find that dream content also becomes less emotionally intense in older age. Despite reduced recall, the dreams that are remembered by older adults often retain rich narrative structure. The dreaming mind continues its nightly work across the entire lifespan. Age may dim memory of dreams while the dreaming itself persists. Newborns spend a huge share of sleep in REM. During the first months of life, infants spend approximately half of their sleep time in REM, or REM-like states. This proportion is far greater than in adults, who spend only about 20 to 25% of sleep in REM. The function of this abundant early REM is not entirely clear, but is thought to relate to brain development and neural maturation. REM sleep may help establish neural connections and calibrate sensory and motor systems. Whether newborns experience dreams in a meaningful sense remains an open question, since their cognitive development is still primitive. What is certain is that the REM state plays a critical role in early brain development. Sleep in infancy is a time of intense neural construction. Human fetuses show REM-like activity before birth. Even before birth, the developing fetus exhibits brain activity patterns that resemble REM sleep. These patterns have been detected through monitoring of fetal eye movements and brain waves. The presence of REM-like activity in utero suggests that the state serves developmental functions independent of external experience. The fetal brain may be rehearsing neural circuits that will later be used for vision, movement, and other functions. Whether fetuses experience anything resembling dreams is unknown, but the machinery of dreaming is operational before the first breath. This prenatal activity underscores how fundamental REM sleep is to brain development. The dreaming brain begins its work even in the darkness before birth. Pregnancy often brings more vivid, emotionally rich dreams. Pregnant women frequently report more vivid, emotionally intense, and memorable dreams than during non-pregnant periods. Hormonal changes, altered sleep patterns, and the psychological adjustment to impending parenthood all likely contribute. Common dream themes during pregnancy include the baby, birth, fears about the child's health, and changes in body image. Anxiety dreams and nightmares may also increase, reflecting both physical discomfort and emotional anticipation. These dreams may serve a processing function, helping expectant mothers work through feelings about the coming transition. The heightened dream activity of pregnancy is part of the broader psychological preparation for parenthood. Pregnancy transforms not just the waking body, but also the sleeping mind. Dogs twitch as dream commands leak past their paralysis. Dog owners often notice their sleeping pets twitching, whimpering, or moving their paws as if running. These movements are believed to be fragments of dream activity, escaping through the normal paralysis of REM sleep. Studies in dogs have confirmed that they exhibit REM sleep similar to that of humans, complete with rapid eye movements and episodic muscle atonia. The content of dog dreams is unknown, but the presence of motor activity suggests that dreams may involve chasing, playing, or other common canine behaviors. Observing a dreaming dog offers a window into the dream world of another species. The twitching limbs and muffled barks hint at adventures we can only imagine. Dogs remind us that we are not alone in the dreaming world. Sleeping rats rehearse mazes step by step in their dreams. Landmark research on rats has shown that animals replay their waking experiences during sleep. Electrodes placed in the hippocampus reveal that the same sequences of neurons that fire during maze running fire again during sleep. The replay occurs in both slow wave sleep and REM sleep, suggesting that memory consolidation happens across sleep stages. The phenomenon provides strong evidence that sleep, and possibly dreams, serve memory functions. Rats rehearsing mazes in their sleep perform better on subsequent trials. This rodent research has been foundational for understanding sleep and memory in all mammals. The running rat in the maze runs again in its dreams. Birds practice their songs at night like lessons. Zebra finches and other songbirds learn complex songs that require extensive practice. Researchers found that during sleep, the neurons involved in song production replay sequences from the day's singing practice. Young birds learning their songs show particularly active replay, suggesting that sleep consolidates vocal learning. The replay occurs without any vocalization, as if the bird is mentally rehearsing. These findings imply that something like practicing or dreaming occurs in the avian brain. The night is a classroom for songbirds perfecting their melodies. In sleep, birds compose the songs of tomorrow. Octopuses show color-changing sleep that looks dreamlike. Octopuses have been observed exhibiting color and texture changes during sleep that resemble their waking camouflage displays. These changes occur during a quiescent state that may be analogous to REM sleep in vertebrates. The displays can be complex, shifting through patterns as if the octopus were dreaming of foraging or encountering different environments. The presence of active sleep in an invertebrate with such different brain structure is remarkable. Whether octopuses experience subjective dreams is unknown, but the behavior is certainly suggestive. Watching a sleeping octopus change color is like glimpsing an alien dream. The dream world may be more widespread than we ever imagined. Some reptiles display REM-like sleep cycles too. For many years, REM sleep was thought to be unique to mammals and birds. Recent research has found REM-like sleep states in some reptiles, including bearded dragons and turtles. These findings suggest that the fundamental architecture of REM may be evolutionarily ancient. Reptile REM differs in some ways from mammalian REM, but shares key features like rapid eye movements and distinctive brain activity. The discovery pushes the origins of REM sleep back hundreds of millions of years. Whether reptiles dream is uncertain, but the physiological substrate is present. The dreaming brain may have ancient roots stretching back to the age of dinosaurs. Elephants sleep little and have sparse REM periods. Wild elephants sleep remarkably little, sometimes only 2 hours per night, and their REM sleep is sparse and irregular. This pattern may reflect the pressures of their environment, where predators and distance to water require alertness. Despite limited REM, elephants display impressive cognitive abilities, including memory and social intelligence. How elephants manage without abundant REM sleep is not fully understood. They may be more efficient at consolidating memories during brief sleep periods. The elephant sleep pattern challenges assumptions about how much REM is necessary. Even the giants of the animal kingdom must rest and possibly dream, if only briefly. Dolphins sleep one hemisphere at a time, making dreaming tricky. Dolphins and other cetaceans exhibit unihemispheric slow-wave sleep, in which one half of the brain sleeps, while the other remains awake. This allows dolphins to continue swimming and breathing while resting. REM sleep, during which the whole brain typically becomes active and muscles become paralyzed, would be dangerous for a marine mammal that must consciously breathe. How or whether dolphins experience REM sleep remains unclear, and if they do have REM, it is likely modified. The question of dolphin dreams is thus deeply complicated by their unique physiology. If dolphins dream, they must do so in ways quite different from land mammals. The sea may hold dreamers unlike any we know. A. I can sketch rough dream images from brain scans. Advances in neuroimaging and machine learning have enabled researchers to decode crude images of visual dream content from brain activity. By training algorithms on brain responses to waking images, scientists can then apply those models to sleeping brain activity. The resulting reconstructions are rough and impressionistic, but still recognizable as categories or general shapes. This achievement was once considered science fiction, but is now a reality in several research laboratories. The technology remains limited and cannot produce detailed dream movies. Ethical questions about mental privacy hover over this emerging capability. Peering into dreams through machines opens remarkable possibilities and profound responsibilities. A wearable device can plant a dream theme and boost creativity. Researchers have developed wearable devices that detect sleep onset and deliver gentle auditory cues to influence dream content. The technique, called targeted dream incubation, can successfully bias hypnagogic imagery toward a particular theme. In experiments, subjects cued with a particular word or concept reported more content related to that theme upon waking. Still more remarkably, dreaming about a cued topic has been shown to boost creative problem-solving related to that topic. The technology is still in early stages but suggests practical applications for creativity, learning, and therapy. Guided dreaming may become a tool for personal development. Simple sounds whispered at the edge of sleep can reshape the world within. Brain-computer links have captured dream answers in real time. The two-way communication established with lucid dreamers has been extended in remarkable ways through brain-computer interfaces. Researchers can now send simple questions to sleepers and receive answers in real time through eye movements or other physiological signals. This has allowed for verification of dream content and testing of cognitive abilities during dreams. The implications for understanding consciousness and subjective experience are profound. Real-time dream communication opens previously impossible avenues of research. The dialogue between waking researcher and sleeping dreamer breaks down barriers once thought absolute. Communication now flows into the depths of the dreaming mind. Targeted dream incubation can steer hypnagogic themes. Targeting specific content during hypnagogia, the threshold state between waking and sleep, is proving to be readily achievable. Devices that detect early sleep stages and deliver cues can reliably influence the imagery that appears during hypnagogia. Users report seeing images related to the word or concept presented to them. This finding opens practical applications for steering the content of this creative associative state. Writers, artists, and problem solvers might use targeted incubation to access new ideas. The technology is simple and increasingly accessible to the general public. Hypnagogia, that fertile doorway to dreams, becomes a garden we can seed at will. The Tetris effect spills game patterns straight into dreams. The Tetris effect is a well-documented phenomenon in which repetitive activities, especially video games, intrude into hypnagogia and dreams. People who play Tetris for extended periods often see falling blocks when they close their eyes to sleep. Similar effects occur with other absorbing activities, from puzzle games to physical tasks. The effect demonstrates how recent waking experience shapes the imagery generated by the transitioning brain. These intrusions are harmless and usually fade quickly after the activity stops. The Tetris effect is a vivid illustration of day residue and the influence of waking activity on dream content. What we do by day follows us into the night. Dreaming can boost creative problem-solving by morning. Sleep has long been associated with creative breakthroughs, and research confirms that dreaming specifically can contribute to problem-solving. People who dream about a problem are often more likely to solve it or find a creative approach upon waking. REM sleep, with its free dissociations and relaxed constraints on logic, may allow the brain to make connections that waking thought cannot. The effect is enhanced when problems are presented just before sleep. Many inventors and artists have credited dreams with inspirations for their work. Strategic use of sleep for problem-solving is becoming a recognized cognitive tool. The answers we seek may wait for us in the dreaming brain. Fever can make dreams bizarre and intensely visual. Illness, particularly when accompanied by fever, often produces unusually bizarre, vivid, and sometimes disturbing dreams. The elevated body temperature and altered neurotransmitter balance during fever affect brain function and sleep architecture. Fever dreams may feature strange transformations, threatening figures, and intensely surreal scenarios. These dreams can feel more real than ordinary dreams, and may be remembered long after the fever breaks. The phenomenon illustrates how sensitive dreams are to the body's overall state. Fever turns the dream generator toward the strange and uncanny. Sickness reshapes not just the waking day but also the nightly theater of the mind. Even with all we know, dreaming still keeps its best secrets. Despite centuries of inquiry and decades of scientific research, the ultimate nature and purpose of dreaming remain partly mysterious. We know a great deal about the physiology of REM sleep and the brain regions involved in dreaming. We have catalogued themes, explored functions, and developed ways to influence dream content. Yet the subjective experience of dreaming, its evolutionary origins, and its full significance continue to elude definitive answers. The mystery of dreaming is humbling for science and inspiring for wonder. Every sleeper remains an explorer of unknown territory each night. Dreaming invites us to continue asking, searching, and marveling at what the sleeping mind can do. And now the quiet wonders of dreams begin to gently fade into the stillness of the night. You have wandered through over 100 peaceful truths about the world that opens when you close your eyes. From the mysterious purpose of dreaming to the brain chemistry that paints your nightly visions. From lucid adventures where you take control to the gentle intrusions of the outside world into your sleeping mind. You have explored the landscapes created by memory and imagination, walked through the science of REM and the threshold states of hypnagogia, and discovered how animals, from twitching dogs to color-changing octopuses, share in the mystery of the dreaming brain. You are part of this story. Not just an observer, but a dreamer, woven into the ancient fabric of sleeping consciousness. Every night, your brain creates worlds that exist for no one else. Every dream is a private theater, a gift from your own sleeping mind to the waking self who sometimes remembers, sometimes forgets, but always returns. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the slow rolling waves of REM, like the gentle pulse of theta rhythms binding fragments into stories. Tonight, as you rest, your brain prepares for its nightly work. Memories will be sorted. Emotions will be processed. And somewhere in the darkness of your sleeping mind, new dreams are already forming, waiting to carry you through the night. You are a small, warm presence within this vast dreaming world, peacefully resting among the wonders. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that every night your mind creates miracles. That every dream, no matter how strange or fleeting, is a testament to the extraordinary power of the sleeping brain. Thank you for joining me on this journey through the world of dreams. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of the sleeping mind. There are more wonders waiting, more secrets hidden in the landscapes of sleep, more mysteries to drift through on quiet evenings. Rest well, and may the gentle presence of dreams keep you company through the night. This has been Drowsy Discovery. Good night.